Hey guys, and welcome to the 14.4 notes. Today we'll be taking a look at the slope of the secant line, which we looked at back in chapter 2, and then turning that into a tangent line using our limit process. So in our example here, we're looking at 2 points P and Q, and the secant line that connects them through the points x f of x and c f of c. Now, as this point Q moves to Q1, still a secant line there, and ultimately then moves and gets infinitely close to P, it becomes then this tangent line. There you can see LT. This is the tangent line versus secant. And you'll recall that this equation is the difference of the y's over the difference or change in x. So our slope of the tangent line, that green line there, is going to be the limit as x approaches c of the slope of the secant line. So coming back down here, the slope of the tangent line is equal to the limit as x approaches c of the slope of the secant line. That's what that expression has there. And in order for the tangent line to have a slope, very important that the limit actually exists. So not only does it approach from left and right the same point, but also that point f of c exists. And then once you have the slope, you can find the equation of that line by then plugging in that point x and y at c. And you'll remember point slope looks like that. So let's take a look at an example here. And we have our equations up at the top here, but we want to find the equation of the tangent line to the graph, or the equation of the line that is tangent, to the graph of f of x equals x squared over 4 at this point. So maybe in our mind's eye we're thinking to ourselves, okay, 1/4 x squared kind of looks like this. And the point 1/4 exists right there. And so what we're looking for is the equation of this tangent line at that point. So the first thing we need to do is find the slope. And the slope of the tangent line is the limit as x approaches 1, that's the x value we're interested in, of the secant, which is the difference of the y's, so x squared over 4 minus 1/4, the y that's of interest to us, over x minus 1. So hopefully you're recognizing this is f of x. This is then f of c, right? The point c, f of c, that we're interested in. Let's see. So the limit as x approaches 1, if I clean this up, x squared minus 1 over 4 over x minus 1 equals the limit as x approaches 1 of x plus 1, x minus 1 over 4 over, you can think of this as x minus 1 over 1 if that's helpful. We get the x minus 1's to cancel, and now we can plug 1 in, and we end up with 2 over 4, because this is just a 1 in the denominator here, so the limit is 1/2. That's the slope of this tangent line. So mt equals 1/2. In order to find the equation of that line, we'll plug it into our point slope. Y minus y equals m that we just found, x minus x. So y equals 1/2 x. If I distribute this, that's minus 1/2, and I'm going to add 1/4 to that. So I end up with minus 1/4, and that seems to resonate with my picture, my sketch over here, which isn't brilliant, but at least I've got a sense of, okay, I've got my signage in order, it's a positive slope, all that kind of stuff. So there's my final answer for the equation of that line. What we're doing here, as it relates to calculus, is finding the derivative. So this new notation, f prime of c, which is, there you go, f prime of c, is the derivative of the function at that point c. And the derivative really just means slope of the tangent line. That's the same thing, just in calculus we call it the derivative. So finding the derivative of a function is find the limit or the slope. Find the slope of the tangent line. So we'll do that for this y equation at that point 2. So the limit as x goes to 2 of this function, it's also a positive quadratic that we're dealing with in this problem, but all I'm interested in is the slope. So let's see, y, 2x squared minus 5x minus y, but I want f of 2. So I'll sneak a 2 in there. So this is f of x minus f of c, and c is 2 in this problem because that's what we're taking it toward, over x minus 2. Now you have to remember to keep writing the limit because you haven't taken it yet, so it's still the limit of this expression. If we clean up that numerator, we're going to end up with 2x squared minus 5x, and then that f of c turns out to be -2, so minus -2 is plus 2. All that's over x minus 2, which is equal to the limit as x approaches 2, because I can't plug in the 2. I have a 2 x minus 2 in the denominator, so that's a problem for me. I got to see if I can factor this. And let's see, the factors of 2 are 2 and 1. I got to get to -5, so that's looking pretty good. And you could probably guess what one of the factors is. If that's the denominator, you're probably going to have one of those in the numerator because you need it to cancel. So don't overthink that one. Don't underthink it, but also don't overthink it. Now that those cancel, I can plug a 2 in, and I get 2 times 2 minus 1 is equal to 3. So the derivative, or the slope of the tangent line, at that point 2 for this function is 3. So I don't know exactly what this looks like, but at 2, that has a slope of 3. That's the derivative. I'm going to skip the graphing example. I'll post another short video when I'm on my computer of how to do the graphing utility to verify that previous answer. So I'm just going to cruise by that one for right now. Another example of finding the derivative, and feel free to pause at any moment here and give this a shot. But in this one, we're finding it at a point C. So not at 2 or 3 or something like that, but at any point C, find the derivative. So this expression that we'll get at the end is going to have a C in it, and then you ought to be able to find the derivative at any point C by just plugging in that point. I'll draw a quick sketch here. Y equals x squared. Not brilliant. Looks like that. So what we're going to find is an expression that, if I plug in that value of c, I should get that tangent slope. If I plug in that value c, I should plug in and get that tangent slope. It should work for any point. So the derivative at c is equal to the limit as x approaches c of the y value, and then plug in c into the function, that's f of c, over x minus c. And as it turns out, the limit as x approaches c, that's difference of two squares, so x plus c, x minus c, over x minus c, those go away, and now I can plug in c, right? As x approaches c, this guy is going to turn into a c, and therefore my derivative is 2c, meaning that if I wanted to find this slope at -2, I would just plug in f prime of -2, which is -4. The slope is -4. And if I wanted to find f prime, the slope, at 3, I would just plug in 3, and that turns out to be 6. So you've got a rule for any value on x squared to find the slope of the tangent line at that point. Now the last name we really call the derivative or the slope of the tangent line is instantaneous rate of change. Rate of change meaning slope, instantaneous meaning at that same point. So all of these things, instantaneous rate of change, the derivative, and the limit of the secant expression for slope, those are all the same thing. But again, in calculus, instantaneous rate of change problems are pretty popular. So in this particular problem, we're trying to find the rate of change of a cone if the radius is changing. So the volume of a right circular cone, if r is changing, find the instantaneous rate of change when the radius is 3. All right. Now, I guess the idea would be you've got a cone and the radius is changing, so all of a sudden it's going from that to that. The volume is increasing, so we're trying to find the rate that the volume is increasing as this radius increases, but keeping the height fixed and all that other stuff. So our equation for this particular height of 6, when I plug it into the volume equation of a cone, gets me this. So this equation, 2 pi r squared, is just a result of taking 1/3 pi r squared h and plugging in 6 for h. But that's the equation I'm going to be using. I'm going to take the limit as r approaches 3. Right? We're getting infinitely close to 3. And the y is 2 pi r squared minus 2 pi 3 squared over r minus 3. The limit as r approaches 3 of 2 pi r squared minus 18 pi over r minus 3. And again, hopefully you're anticipating an r minus 3 factor somewhere along the way. I can take 2 pi and factor that, and I'm left with r squared minus 9. I like that. That's going to leave me with the limit as r, there we go, r approaches 3 of 2 pi r plus 3, r minus 3, lots of difference of two squares, and I get those to cancel. Once I get that to happen, I can plug in 3, and I get 3 plus 3 is 6, times 2 pi is 12 pi. And that is my answer for the instantaneous rate of change of the volume when the radius is 3. So what I've got here is a couple more examples dealing with all, one particular problem here, but we'll try and answer all these different deals here. Let's see if I can add a page. If not, that's okay. Alright, I did it. I bullied my way into that one. I'm sorry. Apologize for the delay. Alright, we'll pick this up. So A, first question here, looks like we're throwing a ball up off a rooftop, standing 96 feet above the ground, and we have an equation that represents the speed. Let's see, it's thrown up 80 feet per second from a rooftop that's 96 high. T is the time that the ball is in the air, and S of t is the speed at that particular time. So a bunch of questions here, many of which are the same in nature. But the first one is, when does the ball strike the ground? And that would be when this equation equals 0. And let's see, I can divide a 16, which is great, a negative 16, let's do that, minus 5t minus, oops, that'd be a 6, which is factorable, t minus 6 and t plus 1. Therefore, t equals 6 and negative 1, but since we're talking about time, I have 6 seconds is my answer there for A. That would be how long it takes for the ball to hit the ground. Question B, at what time t will the ball pass the rooftop? So we're going to set our equation equal to 96. That's how high the building was. And those are going to cancel. And I can divide by 5 again, negative 5. So t squared minus 5t. And then I'll factor t minus 5. So t equals 0 and 5. Well, we knew 0 was one of the answers. That was the initial height. So when does it pass again is going to be at 5 seconds. Question C, what is the average speed of the ball from time 0 to time 2? So that would be a slope of a secant question. So time 0, which we know is here, and then time 2, which is somewhere else on the graph. I don't know exactly where it is, but we're looking for the slope of that. Suppose 2 is there. That's what we're trying to find. So the slope is going to be the difference of the y's, f of 2 minus f of 0 over 2 minus 0. That would be the slope, or the average rate of change, which is equal to, if I plug a 2 into our equation here, so I guess I should say s of 2 instead of f. I'll change that to s. But if I plug in a 2, I get 192. And if I plug in 0, I get 96, which we knew. Over 2 minus 0, so I get the slope equals 48. And that's going to be in feet per second as an average rate of change. I'll come back up here for D. which is instantaneous speed of the ball. So that's just like the derivative, or the limit of that slope equation. Of the ball at time t sub 0. So that just represents any other time. So we're going to solve this in terms of the null t here. So we'll get an answer that has a t null in it. So I ought to then be able to plug anything I want to find these other two answers. Rather than doing this process 3 separate times, we'll do it once to establish the rule, and then I can evaluate it in the next 2 problems. So this is going to be the limit as t approaches the null of s of t minus s of the null t over t minus the null t, which is the limit as t goes to the null of, and I'm going to try and squeeze this in here, zoom in, negative 16t squared plus 80t plus 96 minus, it's going to be that same, but just with the null t, plus 80t null plus 96 over t minus the null t. And yes, it's a bit tedious, but you can't skirt the work here. If we evaluate all this, there's a 16 that can be factored out, or a negative 16 that exists in all 6 of those terms in the numerator. So I'm going to factor that out, and that leaves me with t squared minus the null t minus 5t plus 5t null. That's all over t minus the null t. And the limit as t goes to the null, and let's see, this is a t squared. I'm going to sneak that back in there for the null. I have difference of 2 squares there, so negative 16, and this is t minus t null, t plus t null, minus 5. If I factor out a negative 5, I get another t minus t null there. And let's see, I factored the 16, that was that, and there we go. All over t minus the t null. And this is, yes, a lot of work, but this will then give us the opportunity to find the derivative or instantaneous rate of change at any one point, kind of all at once. Now, because I have this expression t minus t null in the denominator, I can cancel it out with the numerator. But because of the minus sign here, I have to make sure that I can do it to both terms. And by both terms, I mean this multiplication and this multiplication, which I can, which is great. I can cancel those out. So that leaves me with negative 16 t plus t null minus 5. The limit as t goes to the null t. Now if I take t to the t null, so I'm actually going to evaluate the limit here, and think of it as like plugging the value in for x. Like if this were x to 2, you would just plug a 2 in for x. So I'm going to plug a t null in for t, and that is going to get me negative 16 times 2t null, because all of a sudden that's what I'm plugging into that, minus 5. So there's my rule for the derivative we go, equals that guy, or the instantaneous rate of change. Which, now that I've done that in part D, E ought to be pretty quick, because I'm trying to find that instantaneous speed of the ball at time 2. So that's just the derivative at 2, which is negative 16, 2, 2, minus 5. 16 feet per second. I guess this is in feet per second as well. But hopefully no big deal. Now that we have the rule, just pretty quick, just you can fire away and find all those instantaneous rate of changes at these different values. Question F is, again, the same question, but when it equals 0, or excuse me, when is the speed of the ball equal to 0? So actually in this problem, we're going the other way. We're trying to find S prime of what t is equal to 0. So that rule I developed, negative 16, 2t minus 5 equals 0. Gets me 2t minus 5 equals 0 when I divide the negative 16. And then what is that going to be? That's 2.5? Makes that guy equal 0. So at time 2.5, and that's going to be in seconds, that's when the instantaneous rate of change is 0. What that really means is the speed of the ball being 0. We go back to our picture here. For just that brief instantaneous moment in time, that's the top of the arc there, where the ball's just hanging at no speed. We got 2 more questions here that we'll try and wrap up. What is the instantaneous speed of the ball as it passes the rooftop on the way down? And we know that part G from part B as it passes the rooftop. Yeah, it passes the rooftop. So in order to solve G, come do that over here. I am going to use what I know from B. So S prime of 5, and the reason I know it's 5 is because that was the answer to B. After 5 seconds is when it was passing the top of the building again. That's negative 16, 25 minus 5, which is negative 80 feet per second. And what the negative indicates is that the ball is coming down. The speed is 80 feet per second, but the negative is the implication is implying that it's headed down versus when he threw the ball up initially. And then our last question is the speed when it hits the ground, and we know that it hits the ground. That's from part A at time 6. So negative 16, 26 minus 5 equals negative 112 feet per second. Again, that's the speed of the ball on the way down because it's negative at time 6. Hopefully that'll help you guys navigate through your worksheet and the homework questions and come back to class at the end of the period with any questions.